One example is also from the textbook. It looks like this. You have a current I running in a long straight wire, okay? And then here is a metal loop made into a rectangle of length L and width W. Okay? Now, this side is parallel to I, and so is that side. Okay? And there is a distance h between the current and this loop. Now, of course, the current produces a magnetic field, right? It produces a magnetic field which penetrates into the surface of the loop like this, right? And I choose a coordinate system R, pointing directly away from the current. And what I want to know is, if the current changes over time, okay, at a certain rate, say di dt, as a result, what kind of EMF will be generated in this rectangular loop? Okay, that's what I want to know. So you see, as the current changes, of course, the magnetic flux also changes, and therefore there will be an EMF, right? So the key here to this problem is how you calculate the magnetic flux. It will be proportional to the current. So once we get that, then as the current changes, so will the magnetic flux. So we can figure that out. Okay, so let's find the magnetic flux, basically. That's how we want to solve this problem. Okay, the magnetic field lines go into the paper, okay, and the magnetic field have the same exact magnitude for the same value of R. Okay, so let's consider a little strip. Shall we consider a little strip between here and there? This strip is between R and R plus dr. So this width is dr. Okay, this distance is R. Now, the reason why I want to isolate this strip out is because this strip is parallel to the current I, and therefore every point within this strip has the same exact magnitude of the magnetic field produced by that current. Right? In fact, we know exactly how what that magnitude is equal to from Ampere's law. We know B equals what? Mu naught I over 2 pi R. Remember that? Over 2 pi R. Okay, so from that, multiplied by the area of this little strip, we can find the magnetic flux through this little strip, which is d phi b. D phi b will then be equal to B times dA, right, the little area, and this B, of course, I'm assuming that B, you know that B and D have the same direction, so I don't have to use the dot product. B, which is mu naught I over 2 pi R, that's B. dA is L times dr. Okay, so L times dr. This is the contribution to the magnetic flux from this little paper, from this little strip, and then we can integrate from here to there to add contributions of all the strips up, therefore picking up the entire flux. So therefore the entire flux of this. Okay, so let's take the constants out. You got mu naught I L over 2 pi, right? And then the only thing left is 1 over R dr, which we integrate from H to what? H plus W. So it's H to H plus W. Okay, and this of course is a natural log function. If you work it out, it is mu naught I L over 2 pi, and the natural log of upper limit divided by lower limit. The upper limit is H plus W, the lower limit is H, so that's 1 plus W over H. Right? That is phi b. You know it's proportional to I. So as the current changes, okay, so as the current changes, so will phi b. They're proportional to each other. So I know the EMF generated epsilon as the current changes. Epsilon will then be equal to negative d phi b dt. I can easily do this differentiation because all these things are constant except for I. Okay, so I'm going to copy all these constants. Negative mu naught L over 2 pi, right? Natural log 1 plus W over H, and then there is an I which I differentiate di dt, right? Di dt. Now, what does this negative sign mean again? The negative sign tells the direction, okay? The orientation of epsilon. What kind of induced current can it power? Well, let's see here. Assuming di dt to be positive, so the current is what? Is increasing, right? So the flux into the paper is actually increasing. The flux in the paper is increasing, and the EMF, induced EMF in the loop, doesn't like that. It tries to fight against it. So instead of promoting inward flux which is increasing. It wants to promote an upward flux out of the paper, and the only way to do that is by generating a current like that, because that current will give you an upward magnetic flux. Okay, so the EMF will power a counterclockwise current. That's what happens. Okay, now there is no motion for this piece of loop, but another version of the same problem. Okay, I have the same exact setup, but there is a different version, and that version is that I am not changing the current, rather I am pulling the loop down with a certain speed v. Okay, with a certain speed v. Now if I do that, there will also be a changing magnetic flux through the loop. Why is that? Because by pulling it down, you are taking the loop further and further away from the source of the magnetic field, thereby weakening the average field inside this loop, thereby lowering the value of the magnetic flux, right? And there also cause a induced EMF. So suppose I know that both of these, actually the entire loop is being pulled down at a speed v. Can you tell me what is the value of the induced EMF and what kind of current would it generate, clockwise or counterclockwise? Okay, so consider this as a variation of the same problem, the motional EMF. Okay, the first one is not motional EMF, it's just induced, but the second is motional. So here is we call it A, and then version B. Okay, the thing now moves down with the speed v. The current does not change over time. Well, we don't have to start from scratch because we already calculated phi b, right? We already calculated phi b, and the only difference now is that as you change phi b, you find phi b is not changed because of I. I doesn't change. It is changed because there is a motion which changes what? Which changes h. Isn't that true? Which changes h. Okay, h is the quantity that actually changes. W doesn't change, but h does. Okay, so let's see how we can calculate this. I have epsilon in this case equals negative d phi b dt. That's always true, of course. But when I do derivative, I have to be careful this time because I'm taking derivative with respect to h. Nothing else changes. Okay, I'm going to copy these constants. Mu naught IL over 2 pi ddh of this function, which is natural log of 1 plus w over h. Okay, 1 plus w over h. So let me finish this derivative and see what we get. Okay, finish this derivative. So let me copy this constants again. Mu naught IL over 2 pi. Okay, natural log. When you take the natural log derivative, first thing you do is it's natural log of x. First you get 1 over x. This x the whole thing here. Okay, so x is 1 plus w over h, so you get 1 w over h. That's the first thing you get. And then you differentiate with respect to the argument inside, right? So the argument you want to take derivative with is 1 plus w over h. Okay, you take derivative with respect to h for this quantity. 1 is gone, it's just a constant. What do you get? You get negative w over h squared, right? And then don't forget there is also dh dt. Right? All right, let's clean things up a little bit. Right? Let's see. How do we clean things up a little bit? Okay, what is dh dt anyway? It's the rate at which this gap grows, and that in fact is v, right? If we assume, of course, the structure is rigid, and therefore, as you pull the structure down with the speed v, h is going to grow at the rate of v. Okay, so that's something we can copy. We can replace dh dt with v, and then we can do a little algebra here to clean things up a little bit here, and let's see what we get. Okay, some very simple algebra. Just clean this up a little bit and replace dh over dt with v, and you get epsilon equals this whole bunch of constant times v. Okay, so indeed, when the loop is being moved downwards with the speed v, there will be an EMF, and that's the value. What is the direction of the induced current? Is it clockwise or counterclockwise? Well, let's see here. As you pull this thing downwards, again, the field in general gets weaker. Right, through the loop, it's get weaker, and therefore the flux inward is now weaker than before, and as a result you want to maintain that flux going in, so you now need a clockwise current. Okay, so the induced EMF is now promoting a clockwise current, not a counterclockwise current. Now, there is another way to look at this result. What we did here was we basically calculated epsilon from phi b, because we already got phi b. I just took a straight derivative and see what we got. But we can also realize, we can also understand that the reason why there is an induced EMF in this case is because 2 of the 4 edges of this loop is moving, is cutting magnetic field lines, namely this line and that line, right? Both are cutting. So, can we use the motional EMF method to find the same result? Well, turns out, of course, we can do that. All we have to consider are these 2 segments of the loop. This is cutting and that is cutting. Okay? Now, be careful. When these 2 segments are both cutting, they will be cutting field lines in the same direction. Therefore, they will be producing an EMF, each one producing an EMF in the same direction, right? In the same direction. So therefore, the net EMF running in this loop is actually one of them minus the other. Okay, be careful about that. Minus the other. So let's see. This loop, this part of the loop from here to there. Okay, we call it. Let's say we call it segment 1, and here is segment 2. Let's look at segment 1. Segment 1 is really a bar of length L located at the distance h from it, cutting through the magnetic field line with a speed v. At that moment, at that location, we say the magnetic field is B1, okay, produced by the current I is B1. So therefore, epsilon 1 produced by this bar cutting through the field line, we call it B1 times L times what? Times V, right? It's BLV, except B is B1, okay. But epsilon 2, what about epsilon 2? Epsilon 2 is due to that bar, okay, or that segment of the loop cutting the field line with the same exact speed, same exact length. So it's B2 LV. What's B2? B2 is the magnetic field at that location, okay, and both of these will produce an EMF in the same general direction. Can you tell me the direction? The left side or the right side? Which terminal? Which side is the positive terminal? If you think of it as a battery. Well, it is clear that as you cut the field line like that, it's going to cause the electrons to move in a certain direction. Recall how we calculated in a previous example. Okay, how we solve this problem. Okay, you have a bar cutting through magnetic field lines, which of course is in this case is pointing in like this, and a bar is cutting field lines like that. Did we find a way to determine which side has a higher potential? Okay, just look at the motion of the free electrons, right? This is the metal bar, you have a negative charge free electron, here's a negative charge free electron. Okay, this guy is going to be subject to a magnetic force, okay, Q V cross V is like that, so V cross B, okay. V is downwards, V is down, and B is under paper, so V cross B is like that, right? Is like that, but since the charge is negative, the charges are going to move that way, free electrons are going to move that way, so you have an accumulation of negative charge here, and accumulation of positive charge here. Okay, so obviously, this is the where positive charges are congregated, this has a higher potential, this one is a lower potential. Okay, so that's how it goes. And same thing can be said for both of these rods cutting through the field lines, right? So there are 2 EMFs who oppose each other, but which one wins? Well, we have the same L and same V. Just look at B1 and B2. B1 is closer, okay, location 1 is closer to the source than location 2, therefore B1 is greater than B2, so the net EMF would be what? Epsilon 1 minus epsilon 2, right? And it's pointing, epsilon 1 wins, so it's, negative and positive, so it promotes a current like that. That's exactly what we said it would do, right? But what is the magnitude? Epsilon. From this method. I want to see if the method will give you the same result as the previous method, using only changing magnetic flux. This is by cutting field lines. Do we get the same result? Well, let's hope we do. It is this minus that, so it's B1 minus B2, right? Times L times V. Okay, what is B1? B1 is mu naught I over 2 pi R1, mu naught I over 2 pi. These are constants which I take out. What's R1? R1 is the distance between here and there. That's H. Okay, so it's just 1 over H. And then minus the same factor for B2, except it's distance between here and there. So it's H plus W, right? H plus W. And then it's LV, right? L times V. Now, work this out a little bit. What do you get? You get mu naught I over 2 pi W plus H times H, right? And it's H plus W minus H, that's W. And finally, don't forget there is an L and V. Now, compare these two. They're exactly the same. Okay? So we get the same result using different methods. They're conceptually different even though they came from the very same source, which is Faraday's law of induction. This method assumes that we don't deal with the motional EMF thing. We don't worry about cutting field lines. We just say find phi b as a function time and differentiate it. That's all you have to do. Okay, don't forget the negative sign. But the second method is, okay, we use the motional EMF concept. This bar is cutting the field line, that bar is cutting the field line, and we find the net EMF produced by both of these bars cutting the field line simultaneously, and we get the same result. Okay, so it's a neat example how these two different methods give you the same final result.